Okay, corrective maintenance. Corrective maintenance is, of course, repair as needed, but certainly if the cost of repair is within a reasonable say 25%. Otherwise, it doesn't make sense for you to continue to fix something if this something, this repair is going to cost you almost as much as replacing it, right? You will do the same thing for your car. So patient monitors based on solid state electronics nowadays, as I mentioned, you simply replace because there's nothing really you can do inside. Most of the time, you have to wholesale replace the internal electronics anyway. Infusion pumps nowadays is also the same thing, except for a few simple things like replace a door or casket or something like that. The rest you have to basically replace it, okay? And these are the sources of information. I'm not going to go into great detail here. The one thing that I put here to remind myself is that shared experience among hospitals could be something very interesting, and maybe ASPIC can as a center of collecting and sharing information for at least Peru, because this is something extremely useful for everyone to learn from each other, because very often you don't have enough pieces of equipment to perform a meaningful statistical analysis. I'm going to show you a little later the challenge of statistical analysis, and you'll see that if you don't have enough equipment, then you're going to have to wait several years to do something, okay? And Luis may be something you want to think about as well. Okay, so I'm going to ask this question. Why I'm going to talk, I'm talking about evaluation here. Some people say, hey, I use the risk-based criteria. I plan the schedule maintenance. I don't need to evaluate. But our former president in the United States, also a general who commanded the Allied forces in Europe, said many, many years ago that in preparing for battle, I always found that plans are useless at the end, because when the first bullet is shot, things go wrong very often. But planning is indispensable. Why? Because then I know how I need to change my plan. I can go from plan A to plan B, plan C. I know what I need to do. But if I never plan for it beforehand, then I don't know what to do, what to change. So in other words, what I'm trying to say is that good planning and 100% task completion do not guarantee good outcomes. You need to learn from your mistakes and make adjustments. And this is another important lesson here. People think, oh, I planned well my schedule maintenance, I did all my maintenance on time, then patients will be safe. No, that's wrong. Remember when you went to school and you were sitting in class 100% of the time, you never missed a class. Did you learn everything? Why did your teacher had to apply an exam to verify whether you learned something? Because you could be sitting there and daydreaming. So it does not mean that you learn anything. You have to prove, and the proof is in the outcome. Just like medicine, evidence-based medicine is determined by outcome. Okay, so evaluation is an intrinsic part of scientific method. Okay, all right. So how we evaluation? We need to remind ourselves that maintenance is to achieve two things: safety and reliability. Because if the equipment is not safe, we cannot use this on patients, right? And it has to be reliable because equipment has available when it's needed. Otherwise, what's the point of having that piece of equipment? So we have to perform a safety evaluation to make sure the equipment is safe. And also, we need to perform a reliability, what is also known as effectiveness evaluation, to make sure the equipment is reliable. These are two sides of the same coin, okay? It's like medical devices, drugs have to be evaluated for safety because you don't want to give a drug to anyone. Doesn't matter how good it is if it's not safe, right? And it must be effective. It must do what it's supposed to do. This is like, again, drug for treatment of COVID or vaccine for treatment of COVID, okay? You need to prove that it's safe and effective. And that's the similar concept here. Okay, so what we need to do now, I spoke a lot about hypothetical things, theoretical things. Let's do a real work here. The real work here is to understand why a piece of equipment failed, not what failed. Don't tell me that the power supply failed, the electronic board failed, the sensor failed. That does not give me enough information to improve my maintenance strategy. I need to know why it failed. Why? Okay. And why is part of what is called root cause analysis. Now, the full-scale root cause analysis is very challenging, very time-consuming. So I'm going to do a very trivial, simple, first-level root analysis to make things easy for us to do. So we call that simplified root cause analysis, and we will use a failure cause code. So we want to know, oh, this failed, cause of it, and we'll codify that because by codifying that, we can then perform analysis, okay? So this is like evidence-based medicine again. Find ways to address the root cause of the problem and then use the outcome to determine what we need to do. Compare placebo against a real drug. Okay, this is similar to what we're trying to do here. Okay, so what are the causes that we want to understand? And we will use a very small number of causes, as small as possible, because we don't create a lot of cause codes that make the analysis difficult. And again, because you don't have very often enough pieces of equipment to perform analysis. Typically, a hospital has maybe 10,000, 20,000 pieces of equipment, but when you narrow down to individual brands and models, classes of equipment, very often you find yourself with 15, 20, maybe 100, maybe 200 pieces of equipment at most. So if you dilute that in many, many causes, you will not be able to achieve a reasonable analysis, at least at first hand. And then if you want, then you can further analyze in more detail later when you have more data. Okay, so some of the, I'm not going to read every single one, but some are very trivial. No problem found. You schedule maintenance, you go there, everything's fine, you perform inspection, you say no problem found. Unpreventable failure, for example, when you have an electronic that failed, okay, it's unpreventable, nothing I can do about it. Accessory failure, okay, excluding batteries, because battery is a category. Accessories, for example, a pulse oximeter finger probe fail. Rechargeable battery is something that you know well that very often has a problem, and that's something we need to document, and we need to see how we can address that. Network failure. Nowadays, a lot of equipment is connected to the network. If there is a failure in connecting to the network, sometimes the equipment gives the impression that it's not working, but actually it's not the equipment, but it's the network that failed. Use failure. Failures induced by use. Abuse, abnormal wear and tear, accident, someone dropped an infusion pump on the floor. This is not necessarily the pump's problem. It's not cause of a problem. It's just an accident. So that's not relevant here. We separate that. Evident failure, a problem that has been, can be detected, know about it, but did not report it. The user say, oh, I don't care about that particular feature. I don't use it. So, But when you go and perform a scheduled inspection, you say, oh, this part of the equipment is not working. Here come the 4 parts that we are most interested in because that is what we are responsible for. Service-induced failure caused by us or caused by a piece of a part that was replaced and the part failed prematurely. We are human beings. We make mistakes. Don't think we don't ever make mistakes. So we can cause a failure. Hidden failure, failure that the user is not aware of and can come back and harm a patient. The classical example is the electrical safety thing. Although there are really a lot of misconception about electrical safety, I'm not going to dwell on that today. We can talk about some other day. Potential failure, something that is in the process of happening, and we want to make sure that we detect that before it causes a problem. Finally, the most critical one is the one that we need to look for is the preventable and predictable failure. Something that is caused by wear and tear can be predicted or can be detected, and we should do something about it because that's our responsibility. Okay, so let me show you how the data is collected. Okay, bear with me. You need to see this to understand how this thing works. Okay, first, let's take infusion pumps. Okay, in 24 months, we track the service information from the scheduled maintenance. This is basic inspection because there's nothing to be replacing infusion pump. Each bar here is 1 month. There are 24 bars here, and the majority says no problem found. There are a few problems with batteries, evident failure, hidden failure, nothing, potential failure, yeah, maybe a power cord is fraying but has not created a problem, okay? Okay, so that's scheduled maintenance. But how about unscheduled maintenance, corrective maintenance? Oh, wow, see, 24 months, the majority of problems are here, batteries. The users are not charging the batteries routinely, and the batteries are dying before the scheduled replacement time. Batteries have to be replaced, yes, but every 2 years or sometimes 3 years even. But if they die within 6 months of replacement, then they have a problem. And that's when we have the data to go back to the users and say, look, you guys are causing problems here. You need to train the users to keep plugging back the infusion pump to the power outlet. And so these are the things that we find. When we put the two together, we can use a mathematical way to put this together. We call this the probability of finding a particular class of failure. Is the annual failure probability, and then the combination is shown here. In other words, if I pick up a infusion pump at random, doesn't matter whether scheduled maintenance or corrective maintenance, I know these are the likelihood of finding the problems here. The last 4 are the last 4 that I mentioned to you: service-induced failure, hidden failure, potential failure, and predictable, preventable failure are very, very rare. I magnify the scale here to show you that it's very rare, but they can happen and do happen, okay? And also, I forgot to mention that at the end of every 24 months, I calculated a average and standard deviation for each one. So now I can consolidate that for individual hospitals, and I can compare that for multiple hospitals. Now I have another unit called, another piece of equipment called electrosurgical equipment, and I'm comparing now across multiple hospitals. And although they are in different hospitals, they have similar behavior. Somewhat different, random, of course, but they statistically converge to some type of band that we can use to compare notes between hospitals. Okay, so how we use this information? We have 2 groups of hospitals where I used to work, and we have one group of hospital follow the manufacturer recommendation we call OEM, and the other group follow the hospital own procedure and frequency of maintenance for patient monitors. And as you can see, these are totally different maintenance strategies. However, statistically speaking, they are not that different because although the averages are different, the standard deviation bar shows that the deviations are within standard deviation. So it's almost indistinguishable from the statistical point of view, and therefore these two maintenance strategies are equivalent, okay? And this same type of comparison has been done for many other pieces of equipment, as well as different strategies. We have run to failure here, we have statistical sampling here, okay? And the fixed F12 is fixed 12 months annual inspections, okay? So the bottom line here is that there are ways for us to evaluate maintenance strategies to see which one is better. Because the bottom line question is, why should we perform scheduled maintenance if it does not reduce failure or increase safety? Why are we wasting our limited resources to do things that are not beneficial? We could use our time, money, material, etc., to do other things that are part of clinical engineering. Okay, for example, planning, selecting equipment, understanding, help the user understand better the equipment, determine when equipment needs to be replaced, and more recently, the issue of cybersecurity. Okay, we need to help the hospital secure the medical equipment portion of cybersecurity. Is not just IT issue anymore, and so this is something really important. So what I'm trying to say is that, excuse me, clinical engineering is not just maintenance, it's management. And all this here, in the lower part here, is management. So let's not waste too much time doing maintenance if it's not necessary. Of course, we should do what is necessary, but we should also put enough effort into the management of medical equipment. Okay, so let me show you how we perform safety evaluation that I mentioned before. We use the simplified root cause analysis. We assign codes, and then we look at these 4 codes that are the most important ones to see where are the chances we have in terms of reducing the safety issues. Here is data from 10 years of the work that I did with my colleagues at an organization where I used to work from 2004, 2000. Actually, I left 2014, but the data was incomplete 2014. So there are 10 years here to 2013. During this period of time, we had 518 cases of patient incidents. We investigated 90% of it because the rest of the hospital did not allow us to do the work because we were an outsourcing provider. So they were concerned that we could protect ourselves and not give them full information. So, but the rest allow us to investigate. And I should point out that during this period of time, we managed this 10 years, 9.7 almost million pieces of equipment, okay, and performed over 10 million scheduled and unscheduled maintenance here. So this is an extremely small number. At the end of the day, after all this investigation, the ones that we can really conclude that is due to what we call maintenance omission, in other words, hidden failures, potential failures, predictable, preventable failures, service-induced failures, are only 6. Only 6 in 10 million service opportunities. So this is extremely small. It's a solid proof that safety was never compromised by us in this kind of situation. Okay. Here is a more detailed demonstration, but the bottom line is still the same. Only 6 cases here are involved in these four codes here. So this kind of situation is comparable to other institutions, and also this is much better than most manufacturing companies that have the goal of the so-called Six Sigma, okay, which is 3.4 defects per million opportunities. And in commercial airlines, as I mentioned to you before, they are very safe in general, and they are also in the Six Sigma range, okay? And our experience, actually, it's better than Six Sigma. Our achievement was in that decade was between 6.5, around 6.5 Sigma, okay? So it's extremely good, okay? As I said before, safety is one side of the coin. We need to look at reliability. So how do we look at reliability? Again, we want to know the causes of the failures and the amount of failures that are related to these four causes, because these are the ones that we are responsible for directly, okay? So we need to look for the issues and find out what can we do about it, okay? Because if the number of failures caused by these codes here are more than 50% is due to latent conditions that are not due to individuals, but due to our program, then we need to revise the program. Okay, so let me show you some data here. Oh, by the way, just a reminder, a lot of people talk about mean time between failure. And this is a little bit dangerous thinking, because if you don't isolate the failures that are caused by, for example, accidents or by users, etc., then you are not really doing a effective calculation of mean time between failure, because a lot of failures are not due to the equipment itself. Could be due to accessory, due to a user accident or something like that. Okay, so how did we use reliability evaluation? In this case, to make it simple, I pick only one single hospital group, 3 small hospitals in a group. During 3 years, we analyzed a small number of equipment, almost 8,000, corrective maintenance, scheduled maintenance here. And then we analyzed, and then we saw, oh, wow, typically the numbers are single digits, fine, but this one here is double digit, 16 work orders we found with hidden failures. Why we have so many hidden failures here? So it turned out that this was due to a problem that the manufacturer did not even tell us that we need to watch out for. This is one of the type of machine called oxygen concentrator. It's even now used in the pandemic when you don't have a reliable oxygen source. And what we found out that this particular brand and model of oxygen concentrator has a molecular sieve bed that needs to be replaced in theory every 10 years. However, when it's used in a humid and dusty environment, like many nursing homes, then what happens is that this molecular sieve bed will go bad more quickly. So we had to revise the scheduled maintenance strategy by increasing the frequency from 10 years to 5 years, therefore reducing the amount of hidden failures that this was displaying. In other words, we use this to make what we call corrective and preventive actions to change the way we do things, okay? So at the end of the day, we plan, we do, we check, and then we come back and act and revise the process that we do. This is, again, the same thing as the scientific method or the evidence-based medicine that we have mentioned several times before. Okay, so let's go over quickly the discussion and conclusions before we go talk a little bit about COVID. Okay, The service-induced failures are very rare. Okay, most of maintenance errors are actually active failures by human beings instead of latent failures. In other words, accidents, people using the wrong things, accessories that are not good, okay, or not batteries not being recharged, okay. And the reality is that true preventive maintenance is becoming obsolete because technology has evolved very fast. Most of the things now are solid state electronics. So relying on mean time between failure is, as I mentioned before, is dangerous because a lot of failures are not predictable or preventable. So we need to use the evidence-based method to analyze our modalities, and very often there is no reason to follow manufacturer recommendation, even for imaging laser equipment. The reason I say this here is because in the United States, imaging and laser equipment are required by the government to follow manufacturer recommendations, which is really nonsensical, but that's what the government has decided to do. As I mentioned before, in Florence, Italy, the University Hospital Carigi did the same analysis for defibrillators and concluded the same type of opportunities to improve their maintenance there. Okay, so one thing I want to make sure you understand, I mentioned about drugs and vaccines here. Those are the double-blind randomized clinical trials that are used to test the safety and effectiveness of those products, those technologies. However, for maintenance, we cannot do that. Even actually for most medical devices, it's not possible to do double-blind randomized clinical trials because you cannot blind the equipment, you cannot blind the user that easily, you cannot fool the patient that easily with a placebo. So what we do is called in clinical trials something called cohort studies, in which the outcome of two groups of patients are compared, one receiving a certain therapy, certain type of maintenance, while the other did not. But they are not blinded and not randomized. We know who received what, okay? Okay, some people will say that this process, evidence-based maintenance, is very complicated, very difficult to collect the data. It's indeed the case. But should we give it up because it's difficult? No, I don't think that's the case. Like President Kennedy said many decades ago, we choose to go to the moon not because it's easy. Actually, they're hard, but it's because we can get a lot of good outcomes from that if we organize and put our energy resources together to do that. And today, most of the medical technologies are derived actually from the effort to go to the moon, the so-called moonshot, okay? So we do the analysis because it's possible to do the right maintenance in the right way and at the same time at the lowest possible cost. That's why it is important for us, okay? All right, so I'm going to conclude here by thanking my former colleagues and other people who have contributed, but I'm responsible for my mistakes and confusions in this presentation. And Mary, I think we can answer some questions now about evidence-based maintenance before we move on to COVID-19, or you want me to continue to COVID-19, or it's up to you.
Professor, what do you think if we finish with the presentation and after that we do the question and answers part?
Okay, then I will proceed to COVID-19.